So let's go to our final part where we discuss open areas of research. Really, one of the biggest problems that we have to solve in machine learning and AI in general is the requirements for data in compute. So before we were actually asking, someone actually asked, oh, how can we get more compute? And that's actually a great question because we will see that at the beginning in the 1960s when we were starting to get our first computers, computers were very small and there's been an exponential increase in compute capacity. And so also since the beginning, people have started to try to make these computers smart even when they were very simple. But of course, they were limited by the performance of this single computer. Then in 2010, around 2010, two things started to happen. The first one is that this Moore's law of exponential increase started to slow down a bit because now we're getting at the level of kind of physics limits. We cannot go smaller or faster than what we already have. So we're still increasing, but much slower. And the second is that we have kind of a super exponential increase where instead of doubling every 2 years, which is Moore's law, we are now doubling every 3 or 4 months the amount of compute used in the most powerful AI experiments. So not every experiment is that expensive, but the most expensive one has kept increasing a lot. So what happens and how do we do that? One, first is we need to kind of parallelize across servers of computers or also build specialized hardware that is able to do all these operations in parallel. But even if we have these specialized computers, that means we have kind of an exponential increase in terms of cost. So we have now AI experiments taking millions of dollars and also creating a lot of CO2. So the question is, will more data and compute solve everything if we're incurring such a big cost? And there's some players in AI that actually think that that may be the case. So for example, the fleet of cars from Tesla, there's thousands of cars on our roads collecting data because they all have sensors in order to be able to do all the self-driving. And so they're collecting tons of data and they can pull all this data together to improve the self-driving capabilities. Similarly, there's a lab in Google called Google Arm Farm where they have literally 20 arms, 20 robotic arms doing the same task, such as picking an object. A good thing about robots is that, for example, if I make a mistake today and I learn from my mistake, you will not be able to learn from my mistake because I cannot telepathically tell that to you. But robots can pull their data together, their experience together, and kind of learn 20 times faster if there are 20 robots. One issue, though, is that both, you can see that both are kind of only solving one task. This task sometimes is very important. For example, Tesla is learning to drive, that's pretty important. But we would like our robots to be able to do any task or many, many tasks. So actually, we would like our robots to serve as tea or help us move house or do our laundry or clean our house. And my research in particular deals with that, deals with, okay, can we learn to do many tasks instead of just one task? So in particular, the approach is we solve many tasks, then we learn commonalities between all these tasks, and now hopefully, instead of needing thousands of hours to learn a new task, or hundreds of hours, now we can take a few examples and learn very quickly. In particular, our approach takes inspiration, we call it modular meta-learning, and the modularity is inspired by human, which learn and compose concepts in very flexible ways. What do we mean by that? Well, every sentence that I make, you have never heard it before, right? Every sentence is new and you have never heard it, but you have heard every word in my sentence. And somehow, in your mind, you're picking these concepts and you're building them together every time you hear a sentence and understand this knowledge. So that's what von Humboldt was calling infinite use from finite means. Finite means in this case means that maybe we have 1,000 or 10,000 English words, but then by composing them into sentences and composing them into books, we're somehow able to express an infinity of ideas. How do we translate this into neural networks or into robotics? So for example, we would like to tell our robot, move this glass to the table, or find a bottle, then pour its content to a glass, or move the bottle and pour content to a glass that you found, etc., etc. So in this case, now instead of having one neural network, as we were explaining before, now we have kind of composable modules. Each module is kind of a small neural network. And you should think about this each module as kind of doing one simple task. So maybe the blue module, this light blue module is things concerned about moving things, then the dark blue module is concerned about bottles, and the red one is concerned about finding things, and so on and so forth. And now when you want to say, do the task for move the glass to the table, kind of you compose these neural networks together into a super neural network and are able to do these tasks. And now, when you use one neural network, you can use it in multiple tasks, and you don't need to relearn it. So if you get a new task that uses the dark blue, so the bottle classifier, and you already did something with bottles, you don't need to relearn it. And if you need to find something, and you know how to find things, well, you don't need to relearn it to do another task. Cool. So the second type of research you can do also in meta-learning is, okay, what if no one told you the task? So for example, in the case of reinforcement learning that we were talking before about, where we have a robot, it's doing actions in an environment, and then it's getting rewarded for these actions. One thing I didn't tell you is that most of these settings in reinforcement learning actually have very poor reward. That means that these robots get very few amounts of cookie, kind of. So imagine, for example, the task was go to a place I have in my mind in this room. And I don't tell you anything, I don't tell you, okay, I'll give you a cookie when you solve the task, but I will not give you a cookie before that. Now, you would have to kind of move around until you finally found the cookie. Sorry, not the cookie, the place I was thinking about and getting the cookie. If you're a robot, that's even harder because you don't even know how to move. So you start shaking up and then you'll collide with things because you don't know how to move and you will not get cookie, therefore you will not be able to learn. So it's a pretty sad life. So what can we do? Well, we can be curious. So, for example, we can kind of be like babies and reward ourselves, give ourselves cookies when we see something for the first time. So if we go somewhere that we have never experienced before, we reward ourselves, and in this way, we reward behavior that tends to find novelty, and eventually you'll be able to explore and learn things and actually finally get the external reward. However, us as researchers, we don't know how to code curious behavior. So one approach we can do is, okay, what if we search over programs and see which ones leads to curious behavior? Pretty much like evolution did. Curiosity is something in our minds, inside ourselves, that was somehow, it's inside us because evolution kind of put it there because it led to good behavior in the end. However, some programs are not that curious, right? So it will not generate that much internal reward. Some others, also, there's no one way of doing curiosity. There's other ways of getting good behavior. But if you kind of let a computer program randomly, most of the programs that we will do, it will not generate curious behavior, and that's what we actually found. When we let the machine generate kind of thousands of programs for behavior, and we evaluate how good they are at generating curiosity behavior, we find that 99% of them generate very, very poor curious behavior, and only 1% of them actually do generate curious behavior. Not only that, but we can look at the best algorithms that were designed by this machine. We just put a schema, basically it's a bunch of blocks interconnected and kind of that tell the algorithm how to learn. But we simplified it a bit because they take quite a bit of time to explain. This algorithm is actually, even though it looks a bit complex, it's actually surprisingly simple. And it had not been proposed before, and we think it's because kind of researchers said, okay, I don't think such a simple thing can work so nicely. So even though it's pretty dumb, it actually works great. And the other algorithm that we found that it had also not been discovered before, it was so complex that when we looked at it for the first time, we were like, okay, we don't understand what this is doing. Because it kind of uses 3 neural networks, and this neural network is used in 2 different places, so you have to take into account that it's doing the same thing. So it's kind of so complex that we didn't understand it for a couple of months. Then we went to a scientific conference, we talked with an expert, and talking with the expert, eventually after 1 hour, we kind of finally understood what was going on. So if kind of human researchers takes a lot of time to even understand the algorithm, imagine how hard it would be to even invent the algorithm. So it's pretty funny that AIs can generate simple algorithms that we'd be embarrassed to try, and algorithms so complex that we cannot even imagine. And now Maria will tell you about how to train in simulation to avoid the issues of the real world.
So Ferran has told you that one of the issues that we need to solve is how much data do we need to create more intelligent behavior. And some people have thought, okay, you can maybe get a lot of data if the data comes from simulation. And that would be fantastic, right? You have the simulated world, you can actually write in here, you can have as many accidents as you want, they are for free, so you could just practice everything. And this is something that people are really excited about, and there is a lot of work, but let's be honest, simulation simulation is still quite hard, and realistic simulators that can just reproduce all the physics and all the behaviors that we see in our work, that would mean even simulating humans, that is really hard. But it's a really worth path to pursue. And actually, if you think about robotics, there has been also a lot of work, and some of it is very interesting, and I think it's easy to understand, which is they say, okay, our simulators are good. We know that. But what if we just make a lot of different worlds, and we just change a bit of the parameters? Like one world has a bit higher gravity, one has a gravity that is a bit smaller, one, that object weighs a bit more, in one, that object maybe is a bit more slippery. So now, none of the worlds is perfect, but you're going to learn algorithms that can do well on all of them. So that hopefully, when you go into the real world, they still work. And this is some work from OpenAI. It has had a lot of success, and the robot has learned first in simulation, and then it just did the same on the real world, how to solve the Rubik's Cube. So by learning from it in simulation, they were able to get some of the ideas of how moving this object inside your hand should work, so that then in the real world, you can actually improve and solve this task. Of course, it looks a bit shaky, it's not perfect, but it can succeed to do this work, even though it has never been trained with the real robot. It had just been trained with worlds that look a bit similar, they aren't perfect, but they are enough. So this is great, and this is a lot of progress. But there are just one caveat to it, which is that the cube has Bluetooth in it. So that means that it's not a real object. Like, my objects don't have Bluetooth in it. It would be great because if I lost my keys, I would like to just be able to check where they are, but most objects are like this one. So they still require to understand the world by shifting the bit and adding Bluetooth. But we would like something a bit better where actually robots can really understand where the cube is without having to engineer the cube for that. So let me talk about my research. I tried to make robots more intelligent, and one of the things I care the most is how do they interact with the world? How do they really understand how their actions affect? And for that, I think it's really important to think about feeling. How do you feel the world? How do you touch it? And for that, let me show you just very quickly the sensors. Because I think sensors are really important, and we need them to be good. And this is the one that we developed in my lab. This is a tactile sensor. It has 2 fingers. Actually, one of them, you will be able to try like that. It's in here. And what the sensors do is they translate contact into images. The output of the sensor is an image, and when you contact the membrane, the one, you can clearly see how contact appears. Right now you're touching it there, you get the image with the contact. Moreover, there are these black dots, and when you touch the membrane, you might displace them. If you displace the dots and you track that, you can also measure forces, which is also very important because you don't want to squish things, you might just want to touch them or grasp them. So all this information is now available very at hand because it comes from images. And this is something very new. This sensor has just been around for a few years, and now we are starting to explore how they can be used in robotics. So let me show you one of the problems that I care the most with these sensors, which is tactile localization. If I were to tell you now, where is your phone, you probably just try to reach it. Well, you wouldn't go with your eyes trying to find it, right? You just rely on your touch. The same with this, I am looking at you, but I can very easily manipulate the object in my hand. That's because I can do object localization just through tactile. So how would we make robots to do the same? So what we're going to do is have them get those tactile images from the sensors. Let's assume that they know the object they are manipulating. We have the model, we have the shape. And what I'm able to do is actually localize the object. So that would be where the robot thinks the object is inside its hand. So I'm going to show you a bit how we are solving this problem. On the left, you have the real situation where an object is contacting the sensor. Now we have here the point estimation. This is what we would like to predict. And the way we are going to solve this problem is from the sensor, we get a tactile image. And from the tactile image, we use a neural network to try to predict what is the region that is creating the contact. Once we know that, then we can move things into simulation and try to think, let's imagine those dots are actually the sensor. If we are in those positions of the sensor, how would actually the contact look like? So now for each possible pose between object and sensor, you are simulating how contact will look like. And now finally what you have to do is say, okay, one of those simulations in one of those contacts is the one that is more similar to that one. If I find that one, then I will know which one is the pose, which allows me to do type of localization. Let me show you an example of how this works. We're going to start with a tactile image. We are going to predict the region of the object that is making contact. We are going to find the best match, so the contact in simulation that seems more similar to the estimated, and because of that we are going to know the pose. And ideally, reality and estimation should look similar. This is how it looks, and as you can see, as we touch the sensor, we can actually recover the pose of the object inside our sensor, which is what we want. We want to be able to have robots that understand where is the object when they're actually manipulating it. But that's not all we want to do. We want to do even more. So let me just show you briefly some work that my lab made from Alet. The idea here is that you have the robot that has two arms, and its goal, we tell the robot that is move the object, this box, into the blue position. But the robot thinks that the object is in the orange position. So what happens is this. The robot is just going to go, think that the object is in the orange position, so now when it tries to lift it, it's not going to work, because it thinks it's in the wrong position. Why is that? That is because it's not making any use of the sensors. So it has no way to understand the world, no way to react, no way to control its actions, because it has no information. It's just doing some actions that it has been told to do. So what I want to show you now is, what if instead we have this information for sensors? This is only working right now for boxes. Our work now is to extend this to many objects, that way we can localize them in hand. But as you can see, now we do know the position of the object, and because of that, it can succeed to finish its task. So this is what we want, right? We want robots that better understand the world, better react to failures.
Well, we have seen a lot of AI succeed at their task. So one may think, okay, why is an AI taking over the world? So maybe to contrast this a bit, we want to highlight that current AI still lacks common sense understanding. In particular, you can see this top sign here with kind of a few funny patches that are on top of it, but we still classify this as a stop sign. However, this is a case of what is known as adversarial examples, which is a malicious agent has placed these particular patches here in a very careful manner in order to confuse an AI into believing that this stop sign is actually this speed sign. And so now it will believe it's just a speed sign and may crash into a car because it just disregards the stop sign. Note that this AI that's kind of confused by stop signs is very good at classifying stop signs in general. It's just that after putting these patches here, it's very bad at classifying this particular stop patch. But of course, it's still very dangerous in the real world, so it's not ready to be deployed. In a similar way, this turtle here, it was actually 3D printed so that in a special manner with a special pattern of colors, so that the AI actually believed it was a rifle. So one would say, okay, actually you can do the reverse and kind of 3D print a rifle that it looks like a turtle, which again may be pretty dangerous in terms of security reasons. So maybe one of the biggest doubts regarding this and how do we make better AIs is how much structure do we need to put in, and that maybe actually help us to build more common sense into our AIs. And this is maybe one of the biggest debates in the field, which is where do we stand in this line? Do we hard code everything, kind of how we play chess and how we just generated all the computer code, all the code that actually finally play chess, or do we kind of reproduce evolution, right? No one hard-coded humans when we just was this evolutionary process that from the very beginning generated a lot of diversity, and eventually this led to intelligent behavior. Some people, and probably most people in AI, believe there's some priors that we need to put. Maybe we would like to say, okay, there's objects in the world and they interact through forces, maybe gravity exists and so on, so that this helps actually AI learn faster. At the same time, some people also argue that every prior that you put in the computer, it's constraining you to only think like humans, and maybe computers can go further than that. Maybe to end the talk, we'd like to reflect on the dual use of this artificial intelligence and robotics. At its worst, even though AI is a neutral entity, it can be misused. So for example, governments can use it to control people because they can now detect faces in many places around the country, or they could be used for wars. Maybe some more subtle but very impactful that is already taking place is discrimination. So we have a very diverse society, but we still have a lot of bias. And even though AI per se is not biased, if it takes in data that is biased, then it will take the wrong decisions. So for example, imagine we have an AI that makes decisions about about people's salaries. If it has learned from past data that women earn less than men, it may predict that the woman should earn less than men in the future, which is of course a very wrong decision. But it was not the AI's fault, it was the data that was put into the AI. Similarly, if you train as a cancer skin detector for skin cancer only in white people, and then you try to apply it in black people, you may have a lot of issues because it's not the same data distribution, and therefore it may be a very good classifier for white skin, but a very bad classifier for dark skin. However, we'd like to end on a positive note, and we think that actually AI at its best has a huge amount of potential. We have discussed, for example, how AI and robotics in particular can help take care of our elderly. Also, we can use it for medical diagnosis, maybe to help, for example, medical diagnosis in the third world. We can also use it to tackle our biggest challenges, such as climate change, and even help in scientific discovery. We'd like to join us in this very exciting future. Thank you.
About the tactile localization sensor. So if it's comparing the impression that the object makes on the sensor with like a sort of stored set of images, does that mean that it can only really operate with things that it's been specifically trained, like with a set of images, or can it learn how to interact with new things too?
So I'm going to repeat the question. I think from my understanding is that is it only restrained to the things that it has seen before, to that set of images that you already pre-computed when you're doing the comparison for tactile sensing? And the answer is yes and no. So to first degree, the answer is yes, it's restricted to the images that it has seen. But then there are some extra techniques that I haven't shown in here that actually allow you to make some alignments. Those are very local, but imagine that my two fingers, you want to say this finger and this finger are actually the same thing. Well, they more or less are, but you may actually make this match. There are techniques that just allow you to end the matching, so they actually align very well. And that will allow you to have even more opportunities. So that's one of the ways we can actually go beyond the images that we have. But another thing that we need to remember is that because most of those images come from simulation, we can generate as many as we want, for as many objects as we want, almost for free. All we need is to have enough memory in our computers, let's say. So even though that might seem like a restriction, it's actually a very simple one and very easy to just neglect, let's say, because we can very easily generate that data and it's not heavy. So that can be applied to many objects.
There's been a lot of improvements in the mechanical and also in the computing power of robotics, right? In your opinion, how much improvement or where do we stand, what do you guys see in the future of ethics, in regards to ethics? Where do we stand? How much guardrails are to prevent, some of these tools, some of this technology to be used in a harmful way?
So the question was about ethics for robotics and artificial intelligence. So I think Ferran can speak more about the intelligence side. I would say robotics is still in its infancy. So there are, of course, issues to come with robotics. But I would say probably we are first going to have to deal with the issues with artificial intelligence. That I think is something that is already here. We can see it in surveillance and other areas. So my feeling is that many of the issues that come with robots are either going to be very similar to the issues that we already have in industries with machines, like if a plane crashes, who is to blame? If a car hits something, who is to blame? So we already have some policies, some way to deal with these issues. But then when it's about what is the decision that a robot takes, who do we blame for it? I think that goes into artificial intelligence. I think I will pass on that.
Yeah, I think actually ethics at the beginning, maybe when AI didn't work, no one was concerned about the ethics because no one was using it, right? And so it was pretty funny because when we got into the field, maybe 2014 or so, it was starting to work, but kind of not that yet. And now that it's maybe into the mainstream, maybe in the last 2-3 years, kind of you can start to see in the scientific conferences kind of also part of the community that's thinking about ethics. There's kind of many places that you would think about ethics. Maybe some of them are like the bias and fairness that we have talked about before. Some people are like, okay, how do we treat intelligent beings? If there's also intelligence, maybe even if they're made of silicon, do we need to care about this or not? Also, maybe related to ethics is kind of what happens if there's an exponential growth in AI, for example, and this may affect maybe some companies becoming very powerful because for example, imagine if someone controls 10,000 robots that are continuously generating money, that's maybe also a source of inequality. And we need to be thinking kind of very actively about this, right? So there's some people that argue, okay, maybe worrying about superintelligence is kind of worrying about superpopulation on Mars. It's not yet here. And not only that, it's not yet here, but it's so far away that we don't know even how to think about this. But at the same time, there's also some people in the community that says, okay, what can we study here, right? Maybe one of the biggest messages here is that AI researchers should be involved in the conversation, but we need more people than just tech people to be involved in the conversation. And technology is just kind of the tool, and what matters is how do we use it, and both because we can have ideas, everyone can have ideas, not just the tech people that created the tech, but also because kind of everyone will be able to use the tool, and so we have to decide between everyone.
And I'm just going to add that actually, I just remember a case, I was in a self-driving car company talking with one of the CEOs, and that is actually now a big company, or it's still a startup, but it's rather big. And he was joking, actually more than half of these companies, the employees are lawyers. Because self-driving cars, if you do something wrong, you're going to be the one to blame. And they want to make sure they understand what the responsibility should be in each of the cases. So at least if you're in a startup, you really want to make sure that you understand it. And they know it. So they are actually on their way trying to figure out how to solve all those issues. So at least it doesn't hurt on their side. So there is more and more thoughts on this.
Maybe one last one regarding ethics is that right now you have seen that most of what you have shown in terms of AI is neural networks, and neural networks are still not very well understood. And so if you have to talk about ethics, sometimes you have to say, okay, what really happened here? So for example, maybe 1 year or 2 years ago, Uber killed a pedestrian with a self-driving car. We need explanations, right? We need to understand why did this happen. Now, if we have these huge black boxes making the decisions, part of the ethics is, okay, if we don't understand it, we have any real issue. So it's also connected to interpretability and AI, which is still a very big challenge.
I'm curious about your curiosity algorithms. So I was wondering what tasks did you have in mind for them to perform to be able to evaluate this curiosity?
Yeah. So that's okay. Good. So the question was about the curiosity algorithms and in which tasks they were useful. Mostly, so there is two types in which it's very useful. So for example, there is kind of video games where, or the case where I was telling you about finding a place in the room where it's mostly about exploration, right? If you have to find something, you have to mostly explore. And there, your just curiosity pays a lot because it's just trying to explore every little state. However, most of the tasks, we want to achieve a particular goal, right? So if we just made crazy behaviors and tried everything, at the end you would be pretty bad at your task, like, I don't know, making dinner, right? Maybe you want to experiment a bit and eventually know how to move things around, but after you've experimented, now you need to make dinner. But kind of, and most of the tasks are like this, but to a robot that starts making just random actions and doesn't know anything about the world, it kind of needs to be curious for pretty much every task, at least at the beginning, because otherwise it will, just making random actions, it will tend to go into the same place, make the same mistakes, and not learn much, because it will not get any reward, as we were saying before, because it will be performing so bad that it will not make much progress. So we both tested on mostly games or simulated robots exploring some territory, but pretty much any task that you would like a robot to do, at the very beginning it needs to be curious, otherwise it doesn't get from this very bad behavior.
One more question. If you could build any robot without any restrictions, what would you build? To do what?
Okay, I think for me, it would probably be a worker, like a robot who can actually handle people, because you don't want to hurt people, but you want to be able to move them around, and that's usually pretty hard because there are a lot of forces involved, and you need to be strong enough, but at the same time you don't want to be dangerous. So there is a lot of trade-offs in there that I think are super challenging, but I also think it has a lot of value, because we know that we're aging as a population, so if we have robots that can actually solve this problem, that would be a huge advantage. Because also the type of work that humans is not fun to do. So if someone could do that with the right care, with even some empathy, because you need that when you have to take care of someone, I think that would be fantastic. So that would be something that I would like to see happening.
In my case, I thought about the same example. Maybe one thing I'd like to add, when you were phrasing the question about what robot would you envision, one of the things I'm excited about robotics is that it doesn't need to look human to be very helpful. So we are born with one body, right? And this body has to be useful for everything. But one cool thing about robots is that they can be super specialized, and we can have the perfect body, the perfect mind for the task that we would like. And kind of a robot that solved the Amazon Robotics Challenge and was super good at picking, of course, will do nothing like maybe some software robot that will be able to handle humans. And I think that's also a very exciting prospect.